For decades, antibiotics were basically magic. They were the bedrock of modern medicine, turning what used to be a death sentence into a minor inconvenience. We always figured, science would just stay one step ahead. Well, that confidence, it's gone. We're in an evolutionary arms race, and folks, right now, we're losing.
So the big question is, why? How are these tiny superbugs outmaneuvering our most advanced science? Well, the answer really boils down to one thing: a massive, and I mean massive, mismatch in speed. And this right here really gets to the heart of it. Bacteria, they can evolve in minutes, maybe days. Us, it takes more than 10 years to develop a single new drug. It's not even a fair fight. We're showing up to a rocket race in a horse-drawn carriage. There's just no way to keep up like that.
Okay, so section 1, the race we're losing. And let's be really clear about this. This isn't just some catchy metaphor. It's a real, high-speed, high-stakes evolutionary battle. And like I said, right now, we're falling behind.
I mean, think about it. For so long, we had this sense of security, right? This belief that there'd always be a new drug in the pipeline. But that's just not true anymore. That confidence has been completely shaken because resistance is spreading way faster than we can innovate. It's forcing us to rethink our entire game plan.
But here's the thing. It's not just about speed. Bacteria they have a secret weapon. It's this powerful evolutionary shortcut, a tiny piece of genetic hardware called a plasmid.
So, what is a plasmid? Well, the easiest way to think about it is like a genetic cheat code, or maybe a swappable upgrade for a video game character. It's this little circular piece of DNA that floats around separate from the main chromosome, and it can carry all sorts of useful genes, especially genes for antibiotic resistance. And here's the kicker. They can not only copy these plasmids for themselves, they can actually pass them to their neighbors. Okay, so this gives bacteria a massive two-part power move. First, having a resistance gene on a plasmid that has tons of copies, that's like buying a whole roll of lottery tickets instead of just one. It just dramatically increases your odds of a random winning mutation. And then, part 2, when you do hit that jackpot, that one lucky mutation is instantly amplified across all the copies. It's an incredible boost to its power all at once. And look, this isn't just a theory. This is real. Check out this lab experiment. The squares and triangles, that's bacteria with a resistance gene on their main chromosome. As you increase the antibiotic dose moving to the right, poof, they die off. But the circles, that's bacteria with the exact same gene, only this time it's on a plasmid. They barely even flinch, surviving these insane doses. It's incredible proof that where the gene is located makes all the difference. And the power of this amplification? It's just staggering. The study found that a single mutation, just one, was amplified 128-fold when it was on a plasmid. 128 times. That is more than enough to push a bacterium from being treatable all the way past the line to clinically resistant in literally one evolutionary leap. You'd think that's the whole story, right? Well, it gets worse. It turns out that we have been accidentally helping bacteria evolve, and in a way that is completely counterintuitive. This brings us to section 3, the paradox of low doses. Yeah, this quote from a major study in molecular cell pretty much says it all. Sublethal levels. Basically, it means that doses of antibiotics that are too low to actually kill the bacteria, they don't just fail. They do something much, much worse. They actively cause mutations. They make the bacteria stronger. So here's how this bizarre friendly fire effect works. First, you hit the bacteria with a low dose of an antibiotic. Not enough to kill it, but enough to stress it out. In response, the cell panics and produces these damaging molecules called reactive oxygen species, or radicals. You can think of them like tiny bits of shrapnel flying around inside the cell. That shrapnel then damages the bacteria's own DNA, and all that damage leads to mutations. And sometimes, just by chance, one of those mutations creates a brand new form of resistance. The very thing we use to fight it ends up making it stronger. And scientists proved this was exactly what was happening. They ran the experiment again, but this time they added something called a radical scavenger, basically a molecule that mops up all that internal shrapnel. And guess what? The mutations stopped. They even tried it without oxygen, which is needed to make the radicals in the first place. Same result. The mutations stopped. It was the smoking gun, proving our own antibiotics were accidentally fueling these mutations. So, okay,
Let's recap. We've got bacteria using plasmids as an evolutionary supercharger, and we've got our own low-dose antibiotics accidentally causing mutations. Now let's talk about how we help them win. Because it turns out our own behavior is creating the perfect storm for these mechanisms to take over. We're actually creating this perfect evolutionary storm in so many ways, like prescribing antibiotics for viral infection, like the flu, where they do absolutely nothing, or when patients start to feel better and they stop their treatment early. That's a huge one. And then there's the widespread preventative use of these drugs in agriculture, not to treat sick animals, but just to prevent them from getting sick. All of this contributes. And what do all these actions have in common? They create this constant, low-level antibiotic pressure all around us. It's in our bodies, it's in our environment. And that pressure is the exact condition that triggers those radical-induced mutations we talked about. And it creates the perfect playing field for bacteria with those powerful plasmid defenses to survive and take over.
Okay, so understanding the problem is one thing, but what on earth do we do about it? Well, that brings us to the final section, protecting our last defense. How do we turn this around?
I think it's pretty clear by now that we just can't win a head-on arms race. We can't. An enemy that evolves in minutes will always beat an enemy that innovates over decades. So if brute force isn't the answer, we have to get smarter. We have to win with strategy. And that strategy has a name. It's called antibiotic stewardship. And it's really a shift in thinking. It's a commitment to stop treating these medicines like they're a disposable commodity and start treating them like what they are, a precious and finite resource. It means using them only when they're truly necessary and in the right way to protect them for the future.
Because in the end, this isn't just a science problem, is it? It's a social one. The power of our best medicines depends on our collective ability to protect them. So it really leaves us with a critical question to think about. Antibiotics are a shared resource. Are we using them wisely?